All right, next up here, they want us to factor number 15 using complex coefficients. So I see that it's x to the fourth and x squared, so I can just do the usual x box here, just multiplying to negative 25 and adding to negative 24, which would be negative 25 and positive 1. But when I factor this, it's going to be x squared plus 1, x squared minus 25, so that we can get that, that fourth power. So then the x squared minus 25, kind of using our old school factoring, we know we can do x plus 5x minus 5. And then now for the sum of perfect cubes, or not perfect cubes, perfect squares, we can do that as well with imaginary numbers. So just it'll be x plus I, x minus I. I would just think of it, what would it be if it was x squared minus 1 and then attach the I at the end of each parentheses. All right, next up we got some more factoring here. I see this is the difference of perfect squares. So I'm going to do 4x squared minus 9, 4x squared plus 9. And then I actually see that, that this one is the difference of perfect squares again. So it's going to be 2x plus 3 and then 2x minus 3. And then this one's the sum of perfect squares, and so now we can factor that. It's really nice here that we've just done this previous one, because I think of these as really the same, except since this one's adding, it's kind of the imaginary factoring. So it's really the exact same, except the i's are attached out back. So then it does ask for all the zeros here, so we can set each of these equal to 0 individually and solve. So 2x equals negative 3, and x equals negative 3 over 2. This one I can kind of see is going to end up the same, except it's going to be positive 3 over 2. And really all of these are the same, kind of just, except this one will be negative 3 over 2i, or 3i over 2. You can put that I up top or outside. And then this one will be positive 3 over 2 with the I. So once you solve it once, you can kind of just use that to carry you forward if you want. Or if you want to be super sure about it, you can actually solve all of them. All right, this one's asking for intercepts and asymptotes, so it's kind of asking for everything. So if I set the denominator equal to 0, that's going to give me my vertical asymptote, so I can pretty easily see that our vertical asymptote is at x equals positive 2. If you set the numerator equal to 0, that tells you an x-intercept, or multiple if we haven't. So if we have them, so I can see that we have an x-intercept at x equals 6, or 6 comma 0 if you want to do it as a point. And then next up are, if we divide the leading coefficients, as long as they have the same power, that's going to tell us our horizontal asymptote, so that's going to be 1 over 1. So then y equals 1 for a horizontal line. And then our y-intercept is the division of the constant terms. And so in this case, that'll be negative 6 over negative 2, so that'll be at 3. So either y equals 3, or you can put it at 0 comma 3, because it is a point there. So actually, yeah, that's probably better, 0 comma 3, and then the x-intercept would be 6 comma 0. The asymptotes are lines. All right, same idea here on number 18 as number 17, so I'll let you guys try this, same process. All right, number 19 is asking for the vertical asymptotes and x-intercepts. So I'm going to set the denominator equal to 0 to find the to find the vertical asymptotes here. So I'm going to go ahead and factor out a negative x, and that gives me a 3x squared plus 10x minus 8. And we'll do an x box on that. 3x squared, negative 8, and then this will be negative 24 and positive 10. So that sounds like 12 and negative 2. So we get 3x minus 2, and then x plus 4. And so then that would mean that we have 3 vertical asymptotes, one at 0, one at 2/3, and one at negative 4 for our vertical asymptotes. For x-intercepts, we'd set the numerator equal to 0, so that would mean that x squared equals negative 4, and we square root that, and x equals plus or minus 2i. Now those are imaginary zeros, so I would actually say there's no actual x-intercepts. The kind of difference between an x-intercept and a 0 is that an x-intercept where it hits the graph, so I wouldn't include imaginaries on those. It's because it's not actually going to hit the graph there, but those are complex zeros that we have to kind of keep in mind, but we don't actually graph them as x-intercepts. All right, so for this one, kind of like we've been saying before, the x-intercepts is where the top equals 0. And then the y-intercept is the division of the constant terms. So I'll let you guys do that. All right, next up, number 21. So it's asking us where are these true. So I would always graph this to help. And so I see first that this is a degree, if you add up the powers, that's going to be a degree 7 negative. So it's going to be looking like this. And then we have zeros at 0 and at 5 and at -3/2. And this is going to be a bounce and a cut because they come from even and odd exponents respectively. So that one will be a bounce since it comes from the 4th power. And then -3/2, should be like -1.5 there, will be a cut. And then, let's see, positive 1, 2, 3, 4, 5 would be a bounce as well. Okay, so we're going to cut through at -3/2. We're going to bounce there, and we're going to bounce there. And so it's asking us where it's greater than or less than 0, so that's above or below the x-axis. So where is it above the x-axis? I think it's pretty obvious that -infinity to -3/2 was going to be that interval. However, what's not as obvious is that since this is or equal to, I have to include the x-intercepts here, just kind of on an island, since they do satisfy the or equal to. So I'm just going to put 0 there in a bracket, and then I'm going to put 5 there in a bracket. Obviously, the interval in between those is not a solution to this, but those points themselves are. All right, and then next up for the part B, for the less than or equal to 0, that's going to be actually this whole space, because really it's, from -3/2, it's a solution, and it goes all the way to infinity. Because I'm including those x-intercepts, there's no break here, so I'm not going to separate this into different intervals. That whole interval is a correct answer. And it includes all of my x-intercepts, so I don't need to add any individual brackets for x-intercepts because they are included in that interval. All right, next up here, we want to do some subtraction. So we just want to distribute the negative here. So we're going to call that -3 minus 9/2i, and then we're just going to combine like terms. So this and that combine to +1. And then this and this, they have common denominator already, so that's just going to turn into -12/2i. Which is then just -6i. All right, this one wants us to simplify the expression, and whenever it looks like this, it's always a conjugate multiplication that they're wanting here. So I'll go ahead and do that. So on bottom, we can do a flu here since they are conjugates, so that's 2 minus 9i squared. On top, we do need a full FOIL, so it's going to be 52, and then let's see, what is that? So 40 would be 80, so it's 78 plus 26 times 3. Geesh, some big numbers here. 78, okay. So 156. So 156i, and then plus 39 times 3 is 117i squared. So then we know 117i squared we can turn into -117. -9i squared we can turn into +9. Oh, this was a 4 right there, though, because it was 2 times 2. Forgot to actually multiply those. So my bottom is going to be 13. On top, I know I have 156i, but I need to do 117 minus 52 to figure out that real part. So it's going to be 65, except it'll be -65i. Plus 156i. And so now we can reduce these by dividing them both by 13 there. So 65 divided by 13, I know is 5, so this will be -5. 156 divided by 13 is 12, so plus 12i. All right, next up we got some end behavior here. So I see that since this is in standard form, we just look at the biggest degree, or the biggest power, and that tells us it's degree 3, and it is negative. So it'll be going like this. So it's up and to the left, and then down and to the right. So this means that y being negative infinity goes with x being positive infinity, and y being positive infinity goes with x being negative infinity. So A is not that. It's kind of, they're matched up the same. Let's see, on B, negative goes with positive. Yeah, it's got to be B. All right, next up, number 25. This one looks like grouping's going to work, so I'll go ahead and do that. So the first group I can take out 4x squared, leaving me with x plus 1. And the second group I can take out -1, leaving me with x plus 1 as well. So that'll be 4x squared minus 1 times x plus 1, which I can then break down further as 2x plus 1 times times 2x minus 1 and x plus 1. So I see C is correct, and I see that D is correct. Obviously, F and B and A are incorrect. However, E is actually correct as well, because what I can do on this first one is take out a 2, which would turn this into x, and turn that into 1/2. So technically that is a factor of this polynomial. So I have to include that one as well. All right, on this one I want to find the zeros. So I'm just going to do some synthetic division. I'm just going to try out the rational ones that are in here. So I'll start off with 1/2. Let's see, I'm not missing any powers here. So I get 2, 1, 14, 7, 24, 12, 15, and then I already have a fraction there. It's definitely not going to come out to 0, so I know 1/2 is incorrect. Next up, I'm going to skip down to 1, because I'm just going to try out the rational ones here. So I get 2, 2, 17, 17, 34. I can kind of already see this is getting too big, so that's not going to work either. So now I will do -1/2. So I get 2, -1, 14, -7, 10, -5, -2, +1, and 0. So that one did work. So now I'm going to keep going with this, but now when I keep going, I'm going to do it on the leftovers. However, the leftovers on this one I see have a GCF, so I'm actually going to take that out front, but I'm going to need some more space. Hold on. All right, so on this one, I'm going to write this as x plus 1/2. And then I see that these leftovers, I can take out a 2, and that leaves me with x to the third plus 7x squared plus 5x minus 1. And so that's what I'm going to kind of keep going with here. I know D is correct, but now I'm going to try -1 on these leftovers. And so that'll be 1, 7, 5, and -1 from my blue down there. So I got 1, -1, 6, -6, -1, +1, and 0. So that one works as well. So now I have left over x squared plus 6x minus 1. And now I'm going to do quadratic formula and see if the answer is either B or F. So on quadratic formula, we get x equals... let me do this in green to kind of show my work here, my process. All right, -6 plus or minus square root of 36 minus 4 times 1 times -1, all over 2. So we get, -6 plus or minus, and then that looks like 36 plus 4, which is 40, over 2. And then 40 would break down as 4 and 10, which is 2 and 2. So those would leave. 10 is 2 and 5, so I would just write this as -6 plus or minus 2 rad 10. It's not an I there because it's positive, and then we'll just reduce that to -3 plus or minus rad 10. So it looks like F is correct because it's a +3. I need that -3 out front, so I would get B, D, and E on that one. All right, one more here with the conjugate, so 2 minus 3i there, 2 minus 3i top and bottom. So then that'll be a 4 minus 9i squared on bottom with my foo. On top, I need the full FOIL. So I get 6 minus 2i, and minus 9i would be minus 11i. And then plus 3i squared. And so then this turns into -3. This turns into plus 9. So then I get 13 on bottom. I get 9 minus 11i on top. Oh no, this is not 9. This is it's -3 there, so it'll be 3 minus 11i over 13. Technically, in the a plus bi form, we're supposed to split this up into 2 fractions, so I'll go ahead and do that.